Bismillah ar-Rahman ar-Rahim. Today we will start the last unit of this course, which is Unit 6. So in Unit 6, we will cover three topics. First one is modeling of ROMs in Verilog HDL. We already talked about ROMs in Unit 2 at the section of PLDs. So ROM is one of the PLD structure. Secondly, we'll talk about modeling of sequential circuit, and this is the main topic of this unit, how to model sequential circuits. So far, what we covered is modeling of combinational circuits. And modeling of sequential circuit require special attention, so we will talk about how to model flip-flops, how to model registers, shift registers, and counters. And so all of these are special sequential circuits. At the end, we will talk about modeling of a finite state machine. This is any sequential circuit of your design. A small review about read-only memories. We covered this before. So a read-only memory consists of an array of logic devices that are interconnected to store an array of binary data. And usually we draw it like this. So let's say you have, this is a ROM which has 4 words, and let's say each word can store up to 4 bits. So we have 4 bit per word. We need addresses for these rows, so we need 2 bits for that. This is gonna go, we need 2 bits, so it's gonna go from 00 to 11. Each one of these are called address. So for a 4-word memory, we need 2-bit address. This goes as log2 of the number of words. This will give you the bits for the address line. Okay. A ROM is a simple programmable logic device. This is what we covered in Unit 2. And once the binary data is stored in the ROM, so we store the data in here. So we can store this value, any type of data that you can store. And then reading out from the address, if you apply this address, you get at the output your stored data. Okay, so it can read out whatever data you have, but these data cannot be changed because this is a read-only memory. This is not like a RAM. A RAM is random access memory. Usually you write and read to a RAM, but for a ROM, you only read from it. So this data has to be pre-filled. You're going to create a ROM structure, fill your data, and you'll only be applying input to read out any address that you want. Okay, so for example, if you have this ROM, we have 3 bits of input. That means we have 8 words. And then if you look at the data out, the data out here is 4-bit. That means there is 4-bit for each word. So you're going to divide this into 8 rows, and each row is 4-bit. How to use the ROM? If you have a truth table like this, we have 3 inputs and we have 4 functions. So each input combination will match to a value for each of these functions. Okay, 3 bits inputs mean I have 8 words, and the number of functions I can implement is 4. That means this ROM have to hold 4 bits per word. So each ROM has n number of input lines and m number of output lines. To get the number of words in your memory, that's going to be 2 to the n words. Like the previous example, we had 3 bit for the input that translate into 8 words, which is 2 to the 3. Now, how large is each word? This will be determined by the value m. So the word is m bits long. In the previous example, m was equal to 4. We had 4 functions from f0 to f3, 4 functions meaning 4 bits. So this is the value of m. So for in general, you have n input lines, you have 2 to the n words, and you have m output lines, meaning each word is m bits. Okay? And we can use a ROM to implement m functions. So a 2 to the n by m ROM can realize m functions. Each function has to be a function of n variables. So you can just store the truth table inside your ROM. And we also saw how to build this ROM. You know that a ROM will contain a fixed set of AND gates, which is basically a decoder. So your n input lines, which is the address, goes into the decoder, and then only one line of this output will be active at a time. The line that is active will be read out of your ROM. So let's say let's say this is an 8 word by 4 bit. So I have 3, so n equal to 3, that means n is equal to 3. I have 3 address lines. Let's say this goes as 010, so this is address number 2. So this line will be 1, and all the remaining lines will be 0. So all these lines will be disabled, except for word 2. If this consists of 4 bits, now since m in our example equal to 4, that means I will route these values to the output. Okay, so the structure of a ROM, there is a decoder that's taking the address as an input. It will activate one word line, and this word line will allow the output to match whatever is stored in this line. Okay, now for implementation of a ROM, there are a number of ways that you can do it. Actually, we can do it without any special instruction, but let's go over some conventions that will help us create ROMs much easily. Now, we can implement arrays in Verilog, and we have been doing that, but on a different convention. So when we wrote wire 720x, this is creating 8 wires. We have created 8 wires, and each wire will be called by an index, so up to x of 7. But when we declare it like that, we called it a vector. And usually we declare it 720 to indicate that x of 7 is the most significant bit and x of 0 is the least significant bit. And why we do that? If you are using x as a number that's going to an adder or subtractor or any arithmetic or logic function, this is how we define it. It's also allowed to use 720. This will make x of 0 the MSB and x of 7 the LSB, which is عكس الconvention that we used before. If you remember when we talked about, what was it, the multiplexer, we had an 8 to 1 multiplexer. and we said this goes from I0 to I7. When we declared I, we declared it as 0 to 7I. Now the reason we did this because I is not used as a number. This is just inputs to the multiplexer. So these data are not related in uh, يعني it's not a number that I'm gonna compute. So I'm just gonna choose one of those to match the output. So we declare it as I0 to 7. Also, we declared the selection line as S0 to 2 because S will not be used as a number. And this is a selection line. So as a convention هي في النهاية number of wires. If you declare S0 to 2, I will create 3 wires. If you use I0 to 7, this will create 8 wires. Even if you use I7 to 0, I'm also creating 8 wires. تمام؟ فهي في النهاية عبارة عن wires. ولكن as a convention, when I declare it this way, I mean this is a vector. Now, if I declare it 0 to 7, and usually when you want to declare it 0 to 7, يعني as a convention, you put the size after the variable, just to make it easy for whoever is reading your code to know that what you mean by that is this is an array of elements. In the end, they are all wires. هذه 8 wires وهذه 8 wires. But how we use them, I'm going to use X here as a number, which have MSB and LSB. ولكن هنا I'm going to use it as an array. I can pass it to a multiplexer or to any logic that is not using arithmetic operation. For when you declare wire X 0 to 7, that means this will declare an array of 8 elements, and each element is 1 bit each. And we already used these two before. Now, what you can use in Verilog as well is to declare a two-dimensional array. تمام. If you declare X this way, wire 7 to 0, X 0 to 7. What we mean by that, we are making an 8-element array. Each element is 8-bit in length. So this is an array of vectors, and each array element consists of 8 bits. Okay. And this will give me 64 bits in total. You can also use a two-dimensional array. If you declare X 0 to 7, 0 to 7 this way, this will create a two-dimensional array for X. So in the end, like after you synthesize this, in terms of implementation, there is no difference. This is just a convention that we use in writing and using the code. So this will give me 8 lines or 8 wires. This will give me 8 wires. And these two will give me 64 wires. How you name them, how you address them, that's the difference between these declarations.
طيب وش فائدة ذي إن نسويها مرتين؟ ليه ما بنسويها مثلا 64 مرة واحدة ونخلي السايز حقه؟
ايه لانها حتكون اسهل في الادرسنج. مثلا افترض انك انت you are making خلينا نقول a bitmap picture. تمام. تبغى تعطي value، خلينا نقول انها black and white. تمام. image. تمام. black and white. ones mean white and 0 means black. تمام. and you want to store these values in here. image محددة فيها بس black and white and you want to store it. الآن if you want to address this bit, it's easy to go. This is on the x-axis, this is 3, and on the in the y-axis, this is 2. So you can write x3 and 2, and it will give you the value of this bit or of this pixel. أو إنك you write to this pixel. مثلا لما تقول x3 to 0, I want to make this white, so you set it to 1, or set it to 0 for black. If you declare x as 64 bits, now how can you address this bit? Is it easy? No, you have to know 1 2 3 4 5 6 7 8 9 10 حتعد الى ان تصل
يعني لازم
لهذا
تصير
السؤال. So
حفظها.
ايوه so you write مثلا x of 26. تمام. ف when you read your code back، اذا عندك مشكله في الصوره اللي طلعت عندك، آه، تبى تحدد بيكسل معينه، it's hard to read out the numbers. تمام. هذه حتعطيك 64 bits وهذه حتعطيك 64 bits، ولكن how you address them it's easier طبعا depending on your implementation. مثلا اذا عندي register حجمه 64 bits ما اسوي 2D array. صح انه هذا هيعطيني I can still create it, this will give me 64 wires، ولكن it makes more sense for a shift register or a register to be declared as x 0 to 63، او طبعا يعني بالنسبه للregister since register hold number we should declare it as this. تمام. حبدا من bit number 63 up to bit 0. As I said, these are all conventions that we use to make more sense of your variables. Okay. طيب. Why we need that? Let's create a memory ROM and we will see how we can benefit from this 2D array declaration. طيب. So memories, in our case we're talking about ROMs, but memories can also be something called register files. And this will you will be introduced to register files when you take computer architectures, and we also know RAMs, but in our example we talk about ROMs. So we can model it by simply using a one-dimensional array of variables. Array of variables يعني حيكون عندي value هنا, name it anything, and then another value here. This is the number of element for each row, and this is the number of rows. Okay, so each element of the array known as an element, or in case of memories we are talking about words, is addressed by a single array index, and then each word can be addressed or can be one or more bits. Let's take an example of declaring memories. If you declare a 1-bit memory, 1-bit memory means each word is 1 bit. So it will looks like this. Now, how many words you want in your memory? In this case, I want 1024, which is 1K. So this line will declare a 1K words in a variable called mem1bit, and each word is 1 bit in size. So this starts from 0, ends at 1023. Okay, so this is 1K. ليش 1K؟ لأنه 1024 is equal to 2 to the 10, and 2 to the 10 is 1K. Now what if I want to make a 1K memory, ولكن each address will give me 1 byte instead. A byte equal to 8 bits, each word has to be 8 bits, and I need 1K of those, so this should start at 0, ends at 1023. So what we can do is we declare it this way. Wire 7 to 0, mem byte 0 to 1023. So this will come up, يعني to make it in details. This is bit 7, 6, 5, 4, 3, 2, 1, and we need one more, which is 0. Now each word is 1 byte. How many words we have? 1024. So we will declare an array of 0 to 1023. What this line will declare is a 1K 8-bit words. So this is one 1 kilobyte. If you make this 0 to 7, اللي حيصير انه if you want to address whatever in the inside, it's going to be 0 1 2 3 4 5 6 7. تمام. لكن عادة if you're storing numbers inside the memory, you should declare them 7 to 0 to make this most significant and this as least significant. So after you declare your memory, that's going to be your memory, we need to declare the output. This is the output that you read out of the memory, so that's going to be the same size as your bits per word. I have 8 bit per word here, so my output has to be 8 bit. For example, if you assign A to membyte of 63, طبعا membyte can go from 0 to 1023. What this line will do, it will use this 63 as the address. So it will go to row 63, read out whatever value is stored here, and assign it to A. Okay, so this instruction fetches a 1-byte word from the array of membyte whose address is 63, and it will store this value to A. Okay, so the number that we're gonna put in between parentheses here is gonna be the address that we want to read out of this memory. Let's take an example of a complete example of modeling a memory and see how it works. Now, a ROM with n equal to 4 معناه I have 4-bit address, meaning how many words if n is equal to 4?
16.
16. We have 16 word memory. Correct. And m is equal to 3. What does that mean? I have 3-bit per word. If you want to draw the memory, it's going to be this way. I have 3-bit per word, and I have addresses from 0 to 15. Okay. So the ROM stores the result of adding two bits number, x and y, and it needs 3-bit for each word to store the result. Let's write, don't have space to write a complete truth table, ولكن الفكرة إنه عندي الانبut is 4-bit, so number x and y. So I have x1, x2, x1, x0, y1, y0. This is the two numbers. Let's do the whole truth table here. So I have x1, x0, and I have y1, y0. The 4-bit input. And I need, let's call it f2, f1, f0. So this will go from 0, 0, 0 to 1, 1, 1. Let's write a few of them to understand the idea, and then we can, for example, 1, 0, 0, 1, and let's do 1, 1, 1, 1. Okay, now فكرة الديزاين إنه we need a circuit that adds these two numbers and give me the result. And I want to implement it in a ROM instead of any other logic. And instead of creating an adder, I can use a ROM for that. How? الآن here we're adding 0 with 0, the result is 0. Here we're adding 0 plus 1, this should give me 1. For this one, I'm adding 2 plus 1, this should give me 3. And then the maximum you can get is 3 plus 3, which is equal to 6. And 6 is 110. That's why we need only 3 bits for the output. If I wanna design this or implement it in a ROM, I have 4 inputs, x1, x0, y1, y0, and I should have 3 outputs, which is f2, f1, and f0. You can use any combination logic that you want here. If I didn't specify, you can use any combination logic. You can create an adder, you can write the truth table, make it a primitive, you can check a function for each output. You get f2 equal to x1 bar, x0, y1, or كذا كذا. There are so many ways to do that. You can make an adder, 2-bit adder. ولكن you can also implement it as a ROM. Now, if you want to implement it as a ROM, check the number of inputs. I have 4 inputs. That means I need to create a ROM with the size of 16 words. Why? Because this should be 2 to the n, and n here is equal to 4. How many bits for the output? That's 3 bits. So m is equal to 3. So the steps of doing that, first we're gonna declare wires for the whole ROM, and then we're gonna start filling this ROM with data, and then I just assign the output to whatever input I get. Okay, so let's start. Now we are making a module called ABC. We have 2 input line أو two inputs اللي هي x and y, هذه number x and number y, which we want to add, and we have one output, which is the 3-bit output. So I'll declare x as 2-bit and y as 2-bit. Since it's a number, we're going to use 1 to 0, so x1 is the most significant and x0 is the least significant. We already calculated the size of ROM that we need. So we need 3-bit per word, and we have 16 words total. This is the size of each word. This is the number of words. The number of words has to be an array, and this has to be a vector. So I'm going to create an array of vectors. Each vector is 3-bit. How to do it? I'll write wire 2 to 0. Let's call it ROM EX. I have no idea why. What does ROM EX mean? Maybe it means ROM example. So just name it anything. And then how many elements you want? I want 16 elements. So I'll go from 0 to 15. So this will create a 16 3-bit words to declare the ROM. Now for the output, I have 3-bit output, which I'll call it ROM word. 3-bit goes from 2 to 0. Now, the next step here and up to here, this is just filling the ROM with data. Remember that you don't write value to the ROM. I mean, you don't apply an input combination and give an address to write data. No, we only read from the ROM. So we need to fill this ROM. Whoever is using our module will just be reading out of this ROM. It will not write anything. So inside our module, we need to fix or write the values to this ROM. So you have 16 combination and you have to fill each one of them. So you can use assign statement. You say assign rom example of 0. This will point to this element. Each element is 3 bits, so we will assign this as 000. Why 000? لأنه rom example of 0, this is address 0000, and these are the value of x and y, which is coming from the input. So what you're doing here is you're adding 0 to 0, and your 3-bit result is 000. Take this line, for example, which is assigned rom example of 5. 5 is 0101, and this is x1, x0, y1, y0. So this is 1 plus 1. This should give me 010. So check what are you assigning is 010. And so on. You're going to continue using these assign statements up until you reach the final element. Take this for example, rom x of 13. 13 is 1101. So since this is x and y, that's going to be 3 plus 1, which is equal to 4. That means my output should be 4. So this ROM location has to store this value, and this is what we're doing. تمام؟ فهنا the creation of the ROM is completed. Now, how to read the data out of this ROM. تمام؟ and I created this ROM, ولكن user, whoever is using the module, do not have access to these values. ليش؟ لأن this is a wire. This is declared as a wire, and a wire is considered an internal زي ما يقولوا local variable. I have access to the input. أو when you use the module, you can apply input and you get output. تمام? So far we have not touched these yet. All what we did here is to fill the ROM. Now, how to read out? That's going to be easy. We're going to assign ROM word اللي هو الأوتبوت. تمام؟ الأوتبوت ROM word is 3 bits. Have to be careful to make the output the same size as M, and M is equal to 3. So this is going to equal to ROM of X. Now we are addressing our ROM that we created. Inside these parentheses, you need to specify what address you want to read. If you write ROM X of مثلا 10, ROM word will equal to 100. If you write ROM word equal to ROM X of 7, that means ROM word will be assigned the value of 100. ولكن I don't want to fix this number. في النهاية أنا بستخدم memory, فبالتالي I have to apply an address. What's your address? Your address is a concatenation between x and y. ليش؟ لأن x is x of 1, x of 0, and y is y of 1, y of 0. According to your truth table, you created it this way. So that's why you're going to concatenate x and y. You can also write, let's write it here. You can also write assign ROM word to ROM X. You can write X of 1, or you need a concatenation, which is X of 1, X of 0, Y of 1, Y of 0. That's going to give you the same result. So what you do here, انك you try to place the input just as you did in your table. التيبل رسمناه راح علينا, ولكن احنا كتبناه x1 x0 y1 y0. If you did it y1 y0 x1 x0, you should change that to from x of concatenate y first and then x. So it depends on the problem and the truth table that you used. In addition, usually this doesn't change, ولكن in subtraction, if you want to store a value of subtraction between two-bit numbers, this will be different. Okay, so in creating a memory, there are three steps. Step one, declare your input, output, and the structure that you're going to solve, or the structure that you're going to fill the memory in. This is step one. Step two, fill the memory with data. So for each address of your memory, you have to fill data. Step three, assign a value for the output depending on the address. What is the address? It has to be a combination, a concatenation of your input. Okay, any questions? So this is all what we have
واضح.
for the ROM. Um, have you heard about there was ما اتذكر والله اي عام كان, was it Pentium 4 or Pentium 1, one of the Pentium processor had there was a bug that costed Intel about 450 million dollars. كان عندهم طبعا الروم هذه تستخدم زي كذا, مثلا هذا مثال الجمع, maybe it's not يعني that useful, ولكن افترض انك تبي تجمع بدل 2 bit number 4 bit number, تمام, عندك x 4 bit number y 4 bit number, تمام. اذا حتستخدم adder you need a 4 bit carry ripple adder, صحيح, وال4 bit carry ripple adder داخله فيه 4 full adders. Now you connect C out to CN, C out to CN, C out to CN this way. So in order to compute the result of A and B, تمام, you have, وهنا طبعا عندك CN, تمام, طبعا A and B coming to all these full adders. الفكرة في الموضوع انه to get the result here from S3 to S0 and to get C out, the propagation delay عندك have to go through this adder and then you go through this adder, through this adder and through this adder. فافترض each full adder takes in 1 nanosecond to finish computing. That means you're going to get the result after 4 nanoseconds. This is just for a 4-bit adder. These days you're talking about 64 bits. So if you use this kind of adder, you're going to have to wait for 64 nanoseconds to finish addition. إذا استخدمت ROM for addition, like we did in the slide, let's say you're going to have x3, x2, x1, x0, and you have y1, sorry, y3, y2, y1, and y0. What's the maximum that you can get out of this addition is 111 plus 111. So you need, that's going to be 0 carry 1, 1 carry 1, 1 carry 1, and 1 carry 1. Okay, so your result has to be 1, 2, 3, 4, 5 bits. فعندي I will declare the output as F3, F2, F1, F0. كم حجم الميموري اللي احتاجه if I want to implement this in a ROM? Give me how many words and اديني value of n, m, and the number of words. طبعا n هي number of inputs, so this is 8. m is the number of bits for the output, so this is 5. How many words I need?
256.
265 words, which is 2 to the 8. Okay? طيب, I'll create 2 to the 8 rows here. So when I declare the ROM, how to write it? I write wire. First, I'm gonna put the size of each element. So the size of each element is 5 bits. This is ROM. Let's use the same value that they did. So this is ROM X. And then what do I need to put here?
256.
0 to 265. Now you have to fill this ROM using assign statement. So let's take an
هي
example.
256 يا دكتور مو 265.
250, yeah, 256. 256. So this goes to 250, 0 to 255. So you assign ROM X. Let's take an example of um, what ناخذ مثلا let this be zeros to make it easy, and this is 1100. So this is 12. ROM of 12 will equal to 4 bit or 5 bit of 0 0 أو 0 1 1 0 0. تمام اللي هو الاديشن between 0 and 12. This should give you 12. تمام. You're gonna do 256 line of those. تمام. And then you assign the output. تمام. Assign ROM output whatever equal to concatenation between X and Y. Okay, so this is going to be 8 bit. Your address is 8 bit. طيب الآن المقصد من الكلام هذا كله ليش أسوي الآدر بهذا الشكل؟ تمام. This will obviously take so much space. الديكودر عندك 8 to 256. هذا حجم الديكودر. You need 256 AND gates and each AND gate is 8 input. This is huge. ايش استفيد؟ استفيد اني instead of taking 64 nanosecond to compute I will take only 1 nanosecond. ليش؟ لأنه الروم you apply an input and you get an output right away. It's just an assigned statement. تمام؟ ما عندك في الفول ادر كان في عندك propagation. You have to wait for this to compute وبعدين you jump here, you jump here 64 times to get the output. For always remember this for this course and for any computer engineering course. There is always a trade-off between area, speed and power. الباور ما حنتكلم عنه. You're gonna visit it in other courses. ولكن for us there is a trade-off between speed and area. The more area you can take more area to make your circuit faster أو you can save area but you will make your circuit slower. تمام. ف I will pay the price for this area just to make my circuit so much faster. I can add 4-bit numbers in one cycle instead of waiting 64 cycles. Or in 1 nanosecond instead of 64 nanoseconds. This is a huge saving in terms of time. ولكن you have to pay the price and the price is area. طيب طبعا الادر يعتبر بسيط من ناحيه الديلي. الديفيجن احنا we didn't cover division not in 211 ولا في not even in this course ولكن الديفيجن is a process of a repeated subtraction. تمام. فالdivision takes so many cycles to compute. It's the worst of يعني the arithmetic operations. It's worse than the adder subtractor of course and it's worse than the multiplication. تمام. فالdivision في البنتيوم I think it was Pentium 1. I think it was Pentium 1. فإن Pentium 1 they did not create a divider, they did not make a divider to divide numbers, they used ROM structure. كان عندهم ROM. البنتيوم كان was it 16-bit processor? I'm not really sure. Maybe it was 32. ولكن let's say it was 16-bit processor. تمام. 16-bit processor معناته I can add 16 bit number to a 16-bit number. That means n is equal to 32, and this table has to be 2 to the 32, 2 to the 32 wide. So you have 2 um, 2 billion or 4 billion lines in your حجم الروم حيكون بالضبط 4 جيجا بايت او 4 جيجا not byte, it's even more. 16 by 16, this will take يعني 17 bit. تمام. So this is 4 gig of 17 bit. لا دقيقة الديفايدر حيكون 16 sorry. So that's gonna be 16 bit per word. متابعين معايا ولا ضعتوا؟ عشان بس اعطيكم المشكلة اللي حصلت لي.
حاول نلقط.
طيب عيد كده على السريع. In Pentium when they created the division they did a ROM structure. اذا كان حجم البروسيسور او حجم الريجستر في البروسيسور 16 bit معناته you can add 16 bit to another 16 bit number. فحجم الروم هذا المفترض يكون الان تبعه 32. ليش؟ لما تجمع 16 حتبدا من x15 up to x0 بالاضافه الى y15 up to y0. and let's say you're gonna fill a result انه x divided by y. okay let's say this is the case. فمعناته احتاج n equal to 32. حيكون عندي 32 input to my ROM. هذا الروم تبعي 32 bit. تمام. و each word is gonna be 16 bit. فهذا حجم الروم. فحجم الروم هو عباره عن 4 جيجا of 16 bit each. المهم الشاهد في الموضوع انه whoever was designing this ROM ما ادري اذا كان عندهم كات تول ايامها ولكن it probably was. تمام. ف whoever was writing the code for Verilog he forgot one of the lines. طبعا you need to write 2 billion lines that's too much. ولكن الفكره في الموضوع انه جاك هنا عند رقم معين حط زيرو. What happened is one of the scientists was working on a project and he noticed يعني incorrect results وحاول يعني يعدل الكود باي طريقه. لقى انه ما في فايده. فاكتشف انه في بق في البنتيوم بروسيسور. طبعا this is a hardware bug. This is hardware you cannot change it. لانه الروم you cannot write to the ROM, you can only read from the ROM. So if you place zero here no one can change it after you fabricate this chip. خلاص الشيب اوريدي طلعت وصنعت. ف if you divide two certain numbers I don't remember يعني what was the numbers ولكن if you divide these two the result will be zero. This bug cost 450 million dollars. تمام.
لهالدرجة مكلفة يعني؟
طبعا انت بتتكلم انت كم شيب صنعت؟ كم كلفك؟ انت لما يكون عندك ايرور هنا معناته لازم ترجع اي كاستمر اشترى الشيب هذه you have to return it. بالاضافه الى اي شيب صنعته كل الشيب اللي نزل في السوق have to be
تاخذها
returned. اي خلاص
وترجعني.
زباله ترمي في الزباله بكل بساطه. تكلفه تصنيع البروسيسور اتس نوت يعني اتس نوت تشيب. كلفتهم تقريبا يعني نص مليار دولار. بس هذا الايرور جاك واحد هنا نعسان كتب والله بدل ما يكتب assign from x of 12 to 3 bit 100 بالغلط خلاها 000. وجاك التست قال يا شيخ كتبت انا خلاص اكيد صح. ها شوف ايش سوى. ف يعني بس انا يوم تكلمنا عن الرام تذكرت الايرور هذا.
الخطب مليون، ما هو
خطب
مرة صعب.
450 مليون دولار. شوف بالريال كم تطلع. طيب لا هي ايش اللي اخذ سؤال عن لو انه داري عن الموضوع يعني في the first phases of fabrication مثلا وقال يا شيخ ما حد حيقسم الرقمين هذه. ممكن انت بتتكلم عن 16 bit number by 16 bit number يعني the chances that you actually use this value يعني it's pretty slim. ولكن it happened and it costed them. طيب, we're out of time. Um, so inshallah next class we will talk about modeling synchronous sequential logic, الفليب flops والregister والshift registers والcounters before we move into the last part of this course. Okay, any questions?
يعطيك العافية.